fellow mathematicians. Today's video topic has been highly requested, and by highly requested I mean one person requested it, so I guess there's at least some demand for it. So let's go ahead and get started with the video. Okay, today's video will be about recurring sequences. So you might ask yourself, what is a recurring sequence? Well, it's a sequence that's defined by itself. It's recursively defined. So what do I mean by that? Let's start off with the natural numbers, and then you might see what I'm talking about. The natural numbers are constructed as follows. They start off with a 1 or a 0. It depends on what you believe are the natural numbers. So in my opinion, they start off with a 1. So they start off with a 1, and there's a 2, there's a 3, and so far and so forth. Okay, and that's what you might call a sequence. And those terms of the sequence are called members. So the first member is A0, the next member is A1 and A2, and so on. And we can construct every member by another member. So let's just take, for example, the number 3. So number 3 equals 2 plus 1. I hope you agree with me that this is true. And we can write this in terms of members. So A3 is A2, so A2 equals A1 plus 1. Okay, and we can use this type of formula to construct every member of natural numbers. So that means that a member, an plus 1, does equal to an plus 1. So if you want to construct the number 101, that's 100 plus 1. And that's true, I guess. Okay. And that's what you call recursively defined. And now we are going ahead and start with the real problem now. There has been a given sequence an. Okay. And the first member, a1, is defined as 2, and the second member, a2, is called 7, is defined as 7. And the recursive formula for this type of a sequence is defined as an plus 1 equals 1/2 times an plus an minus 1. Okay, how could we deal with that? So we have to find the nth term of the sequence, and after we've done that, we have to find the limit as n approaches infinity. So let's start off with the nth term. How can we find this out? It's pretty simple, actually. If you know a bit about differential equations, it's nearly the same. We are going to solve a difference equation. It's practically the same. You just don't work with derivatives. You are working with sequences, but it's pretty easy still. We have a solution in the end, a general solution, and we can construct this by the roots of the sequence. So let's find out what the roots are. First things first, we are going to start off with the simplest case. We are going to start off with first order linear homogeneous difference equations. Okay, It's pretty simple. You say that some member, an plus 1, is defined as some lambda times an. Okay, what could we do with this information? Maybe we could see what an is. Well, if we take an and use this formula to evaluate an, that would mean that an is nothing else than lambda times an minus 1. And we could do the same for an minus 1. That's just lambda times an minus 2. And we could go on and go on until we reach the last member of the sequence. That would be a0. So we can plug all of this in. So that's lambda times dot 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 times lambda times a0. And how many lambdas do we have? We have 1, and we have n times lambda. So that's just lambda to the n plus 1th power times a0. So you might see a pattern here. And we can construct with this formula also our an and our an minus 1. So let's go ahead and do this. So if we use this formula, we would end up with an equals to lambda to the nth power times a0. And if we use this on an minus 1, that would equal lambda to the n minus 1th power times a0. And now we can plug all of this information in, and we can solve it. Before plugging everything in, maybe we should distribute this 1/2 into this an and an minus 1 and bring everything to one side. So let's start off with that. So that would mean that an plus 1 minus 1/2 times an minus 1/2 times an minus 1 would equal 0. And now we can plug all of those formulas in. So that implies that lambda to the nth plus 1 power minus times a0 minus 1/2 lambda to the nth power times a0 minus 1/2 lambda to the n minus 1th power times a0 equals 0. And the good thing is, all of those a0s cancel out. So this cancels out, this cancels out, and this cancels out. And what we are left with is just lambda to the nth plus 1 power minus 1/2 lambda to the nth power minus 1/2 lambda to the n minus 1th power equals 0. Okay, what else could we do? Maybe we could multiply everything by lambda to the 1 minus nth power. So this cancels out and all of the other stuff cancels out somehow. So that would mean that we got lambda squared minus 1/2 lambda minus 1/2, that's equals 0. And we can indeed solve this equation here. We are just going to use the quadratic formula to solve this. I hope you guys still know how the quadratic formula is working. It's pretty easy. So as you might see, we got lambda squared as the highest degree. So that would mean we are getting two roots, two solutions for lambda. So lambda 1 and 2 are as follows. So that's 1 over 4 plus minus the square root of 1 over 16 plus 1/2. Okay, we can solve this root, so that's 1/4 plus minus the square root of 9, that's a 9, over 16. So all in all that makes 1/4 plus minus 3 over 4. And those are our two lambdas, so we can plug this in. So lambda 1 does equal 1/4 plus 3/4, and lambda 2 does equal 1/4 minus 3/4. So the upper one is just 1 and the lower one is just minus 1/2. And now we construct our general solution. Like I said before, it works nearly exactly the same as for differential equations. So our general solution, GS, is constructed as follows. So a in terms of n is some arbitrary constant c1 times lambda 1 to the nth power plus some arbitrary constant c2 times lambda 2 to the nth power. And now we can plug our lambdas in. So that would mean that c1 times 1 to the nth power plus c2 times minus 1/2 to the nth power. That's great, I guess. So 1 to the nth power is just 1. So we can simplify this further. So that's c1 plus c2 times minus 1/2 to the nth power. And this equation is in terms of n. So that's great because we've got some initial conditions. And we can plug those in, those initial values. And then we are nearly done. Then we have found out the nth term of the sequence. It's fairly easy now at this point. So you just have to take a look what we have to plug in. So a1 equals 2. So a of 1, because that's the index n, does equal 2. So we can plug all of this in. So that means that a of 1 equals 2. And a of 1 is nothing else than c1 plus c2 minus 1/2 to the first power. And that's just minus 1/2. So we end up with c1 minus 1/2 c2. Okay, and now we can bring one constant to the other side and isolate one constant. So let's go for c1. That would mean that c1 does equal to 2 plus 1/2 c2. And now we can plug our c1 into our second initial condition. So let's construct this first. So that would mean that a of 2 does equal 0. And what's a of 2? That's just c1 plus c2 times minus 1/2 to the second power. Minus 1/2 to the second power does equal to 1/4. So we can plug this in. So that's 1 plus 1/4 c2. And now we can also plug our c1 in. So that would mean that 7 is nothing else than c1 is 2 plus 1/2 c2 plus 1/4 c2. And we can bring those together, so that's 3/4 c2. So 2 plus 3/4 c2. And now we can bring 2 to the other side, so that's 5. 5 does equal to 3/4 c2. And now we can divide both sides by 3/4. So that would mean that 5 times 4/3 does equal c2. All we have to do now is plug our c2 into our c1 to find out our first constant, and then we are nearly done. So let's go ahead. So c1 does equal to 2 plus 1/2 times 5 times 4/3. So that's 2 plus 5 times 4/6. Okay, and we can bring this together, so this is 12/6. And that is just 32/6. And then we are done. We are now going to plug this into here, and then we are finally done with our with us finding out the nth term of the sequence. So in the end, what are we going to end up with? Let's plug everything in. So that's 32/6 plus 5 times 4/3 times minus 1/2 to the nth power. And we can simplify this a bit, so we could factor out 4/3. So this makes 4/3 times, okay, if we take this out, that's 8/2 plus 5 times 1/2 to the nth power. Okay, and 8/2 is just 4. So our final answer for the nth term equals to 4/3 times 4 plus 5 times 1/2 to the nth power. And then we are done. That's our final equation. And the last thing we have to do is find out the limit as n approaches infinity. And that's fairly simple. What do we have to do to find the limit of a function? Well, we are going to write that we are looking for the limit of a function. So let's at first say we are going to search for the limit as n approaches infinity of a of n. This does equal to the limit as n approaches infinity of 4/3 times 4 plus 5. And I'm going to write this a little bit different. So we can factor a minus 1 out. So that would be minus 1 to the nth power times 1/2 to the nth power. Okay, why am I doing this? We are just going to take a look at 1/2 to the nth power as n approaches infinity. So we can distribute this n, so that's 1/2 to the n power. And when this approaches infinity, that's 1/infinity, and this becomes 0. So this whole term right here becomes 0. So our final answer is 16/3. 4/3 times 4. So that's 4/3 times 4. And that's 16/3. And yeah, that's it. So that's the limit as n approaches infinity. I hope this helped a bit. That was quite simple. It didn't took me too long because I knew how to handle different equations. If you want more on this topic, I can try to make some more videos. And yeah, if you enjoyed this video, then please subscribe and like this video. And the dog is staring at me. That's kind of confusing. Akiro. That's Akiro. Say hello. If you don't subscribe, this little guy is going to die. No, he isn't. Thank you for watching, and yeah, see you in the next video. Say goodbye, Akiro. Cheers.
Wir kommen auch super miteinander klar. Ist auch ein sehr sympathischer und positiver Mensch.